First of all, thank you, and thank you for the invitation, and thank you to Aziz and to the committee that invite me, Berto, Vilio. So I'm very, very happy to be here, but also a little bit stressed because I'm not from fracture. I'm a manufacturing engineering, so I'm from additives. But at the same time, I think this conference plays a very important role because it unites two things: the process, and then the implications of the process in the lifetime of components. So my presentation will be some framework built by all of some recent students, PhD students. So each of them build a layer of this framework that we are trying to build. So André, it was in 2023, PhD, now in the company. Roya is here and will do a presentation tomorrow in the morning. Roya is more dedicated to modeling, numerical modeling, so very important part also of my presentation. Then João, more recent, dedicated to machine learning, also presenting a part of this framework that we want to build. And Gilles is also here and will be presenting today. And he is the one that has a lot of results for you, with a lot of SN curves to discuss. So my role here is just to present our framework and to try to make some connections about all this work and probably works that each of you in some layer are doing. So that's how I will start. I will start from process physics. So when we begin with this additive manufacturing, so everything that I will show here is about direct energy deposition, okay, for repairing. So this is the focus of our work. The first part will be mainly about deposition, get to know the process, a lot of test and trial, and understanding all the implications between material, process parameters, and what you want to know, melt pool, and then affected area, everything comes from there. And then what we did, we tried to predict something. So we try go to physics to prediction. Then I will show you our multi-scale modeling attempts to try to understand everything. At the same time, we understand that we need to control the process. We need to have actual autonomous control, not just fixed control. In order to, what we want is to have less defects and have a control process. So we went back to machine learning. And finally, we were studying and understanding better the defects to reliability, the work of Gilles. So, but just for a very quick introduction. So what we promise is that AM is, so my title of my presentation is towards sustainability. It's a nice keyword, everybody likes to use this, but we need to understand how it can be sustainable. Of course, if we are talking about repairing very expensive and high-end components, repairing for sure is a very good idea. And AM brings that background that we expect to work. But still, we need to fulfill one main question, is that we keep reliability. So I will present also some particular industrial cases that we've been studying, but mainly you have there the potential. It's better than cladding because we are using laser, so you have more control about the process. We have better control of the dilution, of the heated affected zone. We can also, that's also an important work that we're trying, grade materials, so we can combine compositions in order to have better adhesion and then have bigger hardness in the top. So that's a bonus that we want to find in the additive manufacturing. But then, of course, you have all the structural challenge with fatigue, residual stress, and defects. So the questions of all this is, can we control defects? 1 point, can we predict? fatigue behavior. So when we can answer these questions, then we can really say that repair is sustainable and is an option. So the work that we performed, I present this material. So we're in Cornell as also as a deposition material. We try also an important material that is used for agave web, so for metallization in some repairing situations, because it brings darkness that we need when you're talking about gears. They are cemented, and then we need a layer of high hardness. We don't want to heat treat it or to make all the treatment in all the gears. So we try to deposit this material. And finally, I will present also some work about maraging material. Maraging, because it's very used in additive for repairing some molds, because in Portugal we have a big industry in molds and it's a nice material to use as repairing of these components. So, materials and methods, you have the processing parameters that you could change. You have the laser power, the scanning speed, the feed rate, and also an important parameter, the preheating temperature. So you also use this to understand how we could improve direct energy deposition. So the first question was this. So we try, our first attempt is going to physics to understand what type of defects we will get, how we can improve this. We made a very strong work. This was André, my first PhD student work. We start with the real case, with the industrial real case company that wants to refurbish some components for the wind turbines. I will show, and we did all these attempts that I will detail here for the next slide. So this is a company that prepares shafts and gears from the wind turbine. So big challenge. What we had in the first attempt, we tried to improve the maybe this is have a. Do I have like a, yes, a pointer. Oh, good. So we try to improve the wear resistance. That's why we try this material. So this is a material that has a very high hardness, as we will see. And we try to understand if we could deposit this material on the substrate. So, but what we want when we start experimental work, what we want is to minimize cloud depth, of course, and also get some kind of dilution that guarantees us the bonding that we need. So a lot of experiments until we get these parameters, and then we are analyzing the results, and they were not good because everything cracks. So the results is even with preheating, it's even worse. You can see here the hardness that we got. So this is the substrate. Of course, we get an improvement in hardness, but everything here has cracks. So we could not use this material as directly in direct energy deposition. So, but hardness was very promising. So we tried to go to Inconel. Inconel is much easier material, has very good properties in terms of direct energy deposition. And what we found, a lot of experiments again, but the good thing, we had a very big process window. So we can change the parameters. So power, laser power was one of the most interesting parameters, and so the deposition other feed. And then we see you have very nice deposition with very good microstructure. It looks very good, planar. And then we went to see results in terms of microstructures and also about hardness. And what we get is that preheating is very good. It's very good because it homogenizes a little bit the interface between the deposition and the base material. So we don't have this prone to start cracking. So it was good. but you don't have a very good hardness. So we go to 300 HV. So this was good for filling, but not good for the last layers, because you don't have the hardness that we need. So what we think about grading, because it's interesting. But before grading, we try to do like big parts in Inconel and understand a lot of things about because you do a lot of layers, you are again imposing new thermal conditions, and then we want to understand if we get good results, and also on the interface. This is also a point. So we try to do a lot of tests, and we did these tests in interface, and we got very good results. The material fails in the bulking panel, and we got these results for the test. Important points, we get the same result as like porous steel, so we have the same type of yield strength, and it have good good utility. This is good for material, for this type of application. So this was a good start. So you could make the bonding, and you have good mechanical properties. We didn't have the hardness that we need for this type of applications, because the goal was for the gears. Then, so you have the hardness, and you, as expected, the wear behavior was not so good, was as we expected. So then we think, why we don't mix the two materials, and we try to see if we get an improvement in hardness. So we did it like we show here. We try 100% in the base of Inconel, then start to adding a little bit of metacoal, the hard material, and then we go until we have the final layer totally hardening material. The conclusions is not very clear here. You have all the layers that we try to do, is that after 50% we don't get good depositions, you get cracks. So we understand that this is the maximum content that we could use. So then we were studying these materials. We start doing also again the same thing, build some bulk additive parts, and also studying the interface, and the conclusions were interesting. So what we get is we get almost the same properties than Inconel, and we didn't increase the wear behavior, so we get the same hardness. So this is not very interesting, but at the same time, for the company that we were working, it was a quite interesting solutions because of the price of the materials. The metacoal is a water-atomized powder, so it's very cheap. So the idea is that you could replace 50% of the Inconel with this and getting the same properties, because we see here we get a little bit less ductility, but we could still have good properties. So this is what the company choose to wear, and with good results. So not for the gears, because we have no hardness in the surface, but we have for the shaft, we had good results with 7% less costs. So the challenge was now to go for the gear parts. The company even installed like induction heating for the preheating, but with this material we could not get the results. So conclusions of this work. This was the first part. Material limitations, Inconel works, FCM has limits, we got these limits, we validated in shaft components. But the main point of this work is because at the same time, we were trying to understand all these, we did a lot of experiments, a lot of characterizations, and all this work was used in the next steps by the modeling and also by the control layer of this framework. So in modeling, what we try to do, we try to build this very nice framework where you go from thermomechanical modeling, so macro scale modeling, and then you go to dendrite solidification, secondary phases in case of Inconel is very important, and then predicting hot cracking. And finally, if you can use everything like this, you can maybe achieve some indications for fracture behavior. So this was the numerical framework that we tried to develop. So dendrite, segregation, precipitation, and send some information about strength. So first step, and with the results that we have previously, the experimental results, we build this macro scale application where the inputs are the process parameters again, and then you have the outputs, the cladding morphology that was validated with previous results, the thermal history, and the residual stress. With this, the ambition gets bigger, and so if you have the thermal history, why not go to the microstructure and try to modulate the microstructure behavior? So we try this, and we get some good results for the primary dendrite arm space. But then we find out that Inconel has a very complex material, and it segregates some phases. So we need to go one scale ahead, and we go for the macro scale, nanoscale, I think, to do the precipitation modeling. So this is quite interesting because we could also make some validation. And this is important because then you can understand where the component, or where is the ability to form cracks. And then you go back to macro scale, and then we have everything to try to model the crack behavior. Finally, the ambition got bigger and bigger, so we try to go to join everything and go to fracture behavior. That is important part. We don't try to model the crack. We try to model the stress concentration, the weak interfaces, and with that understand the prone to fracture. Okay, so this tries to link all the fields. So the next step was try to we understand we will always have fails and defects. So if you always have fails and defects, the first problem that we should try to address is control of the process. My field, I'm not, I start in casting. So casting is a very uncontrolled process. I'm from casting technology. And when this trend of additive manufacturing came, I think, oh, this is perfect. I can control layer by layer the casting and the morphology. We can do a lot of things, but no, it's still a very complex process with everything happening. But at least we can have more information, and that's what we try to do. So we try to put more sensors in the process. We try to implement a new monitoring system, and then try to make autonomous control, so closed loop. So this is another work that we've done, and in order to have some credibility, we try to do this in 2 different places. So at Energy, where we did all this work with our installation. This is our installation for cladding, but also in Plenary, in some collaborations, we try to implement the same thing. So the same system with different cameras and different, so you had a camera on axis, and you have a very expensive camera off axis that gives us a lot of information. The first step, sampling. So all the things that we're doing before work are the results here that we try to make a data set with that sampling. So I think this is like in parallel work. The same work was used to do these samplings. Then we could understand the relation between what we are doing and the image from the cladding. So this is the control factor that we try to implement. And then implement this monitoring model that tries to, it starts with an image, but then it compresses to a very simple vector. So embedding all the information. And then it can also reply again to another image. A very important part of this work is that we could teach one of the sensors that is very expensive, you cannot use it all the time. We could teach the other sensor that is on axis and very cheap to understand what he's seeing. So this allowed us to use only this very simple sensor. And with this is just for monitoring. So we know what we want and we say that is okay or not okay, but then we try to go to the control. So we use all this data that we have to offline train this controller. And with this, of course, this is valid in this range. We could actually build a control system based on image. So we could get these good parts with live control, let's say like this. And this was also a very important part of the work. So after this, we try, then comes Jill with all these work to do to understand the impact of the process on the properties to fracture. So we try to go from defects to structural reliability. That's why everybody's here. So only now I'm showing some nice curves. So this work, we changed here, we had to change material because we had another challenge there. We changed to maraging steel. This is another important application for repairing. So, for example, big molds use H14 as a base material, and one of the materials that is very competitive with that, and is very easy to depositate is maraging steel. So we try to understand what happens with this material. Again, we knew that the part that we need to understand is the manufacturing, because cracks will be initiating by the defects that comes from all the process. Also, the deposition strategy will influence the defects, and also the interface, as we see. And this afternoon, you can see a lot of details of this work from Jill. So we did amazing work with a lot of experiments with different type of samples and a lot of depositions, so with heat treatment, not heat treatment. So it was huge work to understand all this influence. So I will show you very, very quick resume. So the main conclusion, so you have all the results here. Of course, it's the correct propagation is totally dependent on the building direction, so is direction dependent. For example, the base material has influence. We understand that we also did some B material samples where we could understand the influence of the B material. So it alters also the crack path, but also the scatter of all the results is, as you can see. Then the maraging, as you know, it's a material that we usually need to treat. We did the heat treatment, and after that, so we understand that the anisotropy is lowered. So this is a good thing. But then when you go to fatigue life prediction, you see in the first slide, for example, one conclusion that was not so evident is that the heat treatment doesn't improve the fatigue life. So this was one thing. Also the scattering again. But then when you go to the normalized results, you understand that we can normalize this, and then you have only the fatigue life governed by defect. So material is not so important. Material state is not so important. But we understand that we cannot predict. So defect in this, even if you minimize, if you reduce everything, is still quite statistical. So then we try to make this design framework where we base our predictions on some characterization of the defect population, then also identifying the critical defense, and then applying the laws as we know. Of course, this may see a little bit not connected, but everything that we are, these blocks, all the data, all the information, all the predictions are trying to be put together in order to have like a big framework of all this. So you have modeling, you have control, and now you have fatigue prediction. So for resuming the key findings in this layer, so fatigue is governed by the biggest effect. Macro, of course, is microstructure dependent. Scatter is what we get, but my big conclusion is that reliability begins on the process, and that's my field. So when you are repairing, you need to look at the process and define the design of the repairing process is a constraint that you need to account in order to predict your component life. So this is just one final proposal that I have here. This is a work that everybody is listening about, the product passport. For everybody's talking about that for factories, but I think for repairing is also an important topic, because if you're repairing, you need to get all the data from your part, the previous part, the number of cycles that is being used, and then the repairing data. With this, we can always understand where is your component. So you have all these inputs that you can use, and then we try this very simple example with one repairing part, a small part there. So if you can use an ID for your part, track all the information that you use from the base component to all the depositions. So you have the nice chart that everybody wants to look. So you have material savings, you have energy reduction. That's the good part. But most important is to keep all the data and to use that in next step. So finally, everything that I was trying to present here, a lot of information, a lot of different subjects. But to resume is that everything starts from physics. You have the predictive model, you have the real-time control. This everything trying to predict defects and help in the reliability quantification. And all of that should go to a certificated, and the process digital passport, product digital passport, I think could be a really good tool for this. So that's my presentation.